Quantum physics is strange. It's the kind of science that makes even the smartest people scratch their heads. Imagine a world where a single particle can be in two places at once, where things don't exist until you look at them, and where tiny objects can pass through walls. It may sound like science fiction, but it's real. That's the world of quantum physics. The world around us seems normal. A ball rolls when you push it. The sun rises and sets. Light turns on when you flip a switch. But deep down, at the smallest level, smaller than atoms, the rules change. Suddenly, particles start acting more like waves. They move in unpredictable ways. They can be linked across space in something called entanglement, where changing one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance. Even stranger, quantum particles don't settle into a clear state until someone measures them. Until then, they live in a kind of blur, like flipping a coin and it being both heads and tails until you peak. Why does this matter? Because quantum physics isn't just weird, it works. It's the science behind lasers, smartphones, MRI machines, and even the computers we use today. And it's opening the door to new tech, like quantum computing, that could change everything. Quantum physics is confusing, no doubt, but it's also beautiful, powerful, and oddly thrilling. It reminds us that the universe is far stranger than we ever imagined. And that's exactly what makes it so fascinating. At the turn of the 20th century, science was proud. It had built a solid house on the rules of classical physics. Gravity worked. Newton's laws explained motion. Electricity and magnetism were under control. The world felt almost complete. But something strange was flickering at the edges of understanding, a glow that wouldn't behave. It all began with something very ordinary, a metal stove glowing red when hot, a piece of iron turning yellow, then white. This glow, called black body radiation, came from objects heated to high temperatures. Scientists thought they could explain it using the rules they knew, but every time they tried, the numbers fell apart. They expected the glow to spread evenly across different colors of light. Instead, it peaked at certain colors depending on temperature. Worse, when they used the old equations, the math predicted something ridiculous. It said the object should give off infinite energy in the ultraviolet part of the spectrum. That meant any hot object should burn the world with invisible rays. But that never happened. The world stayed calm. The math was clearly broken. This problem became known as the ultraviolet catastrophe. It was one of the first cracks in the wall of classical physics. A German physicist named Max Planck took on the challenge. At first, he believed in the old rules. He tried every trick he could think of to fit the math to the glowing light. Nothing worked. Finally, he did something desperate. He stopped trying to explain why the energy came out the way it did. Instead, he tried a new kind of math. In this new math, energy wasn't smooth. It didn't flow in a steady stream. It came in tiny packets, jumps, bursts. Planck called these packets quanta. They were like the smallest sips of energy that could be taken in or given out. He did not like this idea. It felt wrong, but it worked. It matched the glow exactly. Planck had no clue what it really meant. He only knew it solved the problem. He thought maybe it was just a math trick, but it wasn't. It was the first step into a new world. A few years later, Albert Einstein picked up Planck's strange idea and ran with it. He used it to explain another mystery. Scientists had noticed that when light shined on a metal surface, the metal sometimes spit out tiny particles. They called this the photoelectric effect. But the old theory said brighter light should always knock out more particles. That wasn't what happened. Only certain colors of light could do it. Even a dim blue light worked better than a bright red one. It was confusing. Einstein said, maybe light isn't a wave like everyone thought. Maybe it's made of packets too. Little bundles of energy. He called them light quanta. Today, we call them photons. Each photon had a certain amount of energy based on its color. Blue photons had more energy than red ones. If a photon hit an electron with enough energy, it kicked it out of the metal. If not, nothing happened. Even if the light was very bright, that explained everything. And it meant something shocking. Light behaved like a particle, just like matter. But light also showed it could act like a wave. It could bend. It could interfere with itself, just like water waves do. Scientists ran simple experiments where they sent light through two slits in a screen. On the other side, they expected to see two bright spots. Instead, they saw a pattern of many light and dark stripes. That only happens with waves. Even when they sent one photon at a time, the pattern still built up over time. The photon seemed to go through both slits at once. It interfered with itself, like it was a wave. But when they tried to measure which slit it went through, the pattern disappeared. The photon acted like a particle again. This strange behavior had a name: wave-particle duality. It meant that light was not just a wave, not just a particle. It was somehow both, depending on how you looked at it. That was not just weird, it was world-shaking. Matter would later be found to behave the same way. Tiny bits of stuff like electrons showed wave behavior too. These discoveries were not small details. They were cracks that shook the whole building of classical physics. They said that the rules we thought were solid were not true at the smallest scales. A new kind of physics was needed, one that could handle particles acting like waves, energy coming in bursts, objects changing behavior just because we tried to observe them. That new physics would become quantum mechanics. Why does any of this matter? Because it changed how we think about reality. We used to believe the universe was a giant machine. You give it the right push, and it moves in predictable ways. But the quantum world doesn't follow that logic. It says that sometimes things happen without clear cause, that particles can be in many states at once until we look, that even the act of watching can change what we see. These ideas are not just theory. They affect our everyday lives. Lasers, jeeps, computers, medical scans, all of them depend on quantum principles. Without those early mysteries, those impossible problems, none of this would exist. This is where the story begins, with scientists facing a puzzle no one could solve, with one man daring to change the math, with another seeing the truth in that change, with simple experiments that refuse to obey common sense. The journey into quantum physics starts with questions about color and heat, but it quickly leads to deeper questions about what is real, what we can know, and how the universe behaves when we are not looking. In this video, we will meet the strange quantum world. We will see particles that dance with uncertainty, experiments that defy logic, theories that sound like science fiction but turn out to be true. The quantum story is full of mystery, but it is also full of wonder, and it all started with a glow that no one could explain. Step into the quantum zoo. It is nothing like a real zoo. There are no cages, no fences, no signs telling you what not to touch. You do not walk through it. It moves through you. Or rather, you are already inside it. Every single thing you see and touch and breathe is built from the creatures that live here. You just cannot see them, but they are always there. Let us start with the basics. Atoms. For a long time, we imagined atoms like tiny solar systems, a solid center, called the nucleus, with little electrons spinning around like planets. It made sense. It felt familiar, but it was wrong. That model was only a picture, not the truth. The real atom is stranger than that. The nucleus is real. It is tiny, very heavy. It stays at the center. It holds protons and neutrons. But the electrons do not spin in neat circles. They do not act like tiny marbles. They do not even have fixed paths.
They are more like clouds, thin and ghostly. Their location is always a maybe. You cannot point to one and say, here it is. You can only say, it is probably in this area. That brings us to the electrons. These are the quantum dancers. They follow rules no one ever expected. They jump between energy levels without crossing the space in between, like skipping rungs on a ladder without touching any. They can be here, then there, then somewhere else, all without warning. When you try to find out where they are, they become shy. The more you try to know their position, the less you can know about how fast they are moving. And if you try to know their speed with perfect accuracy, you lose track of where they are. This strange limit is not because your tools are bad. It is not about human error. It is built into the fabric of nature. It is called the Uncertainty Principle, and it means you can never know everything at once. Now, let us meet another strange resident of the quantum zoo, the photon. It is a tiny packet of light, not a wave, not a particle, or rather, it is both. Sometimes it acts like a wave. It spreads out. It bends around corners. It can create patterns, just like ripples in a pond. Other times, it behaves like a solid bit of energy. It travels in a straight line. It knocks into things. It gets absorbed or reflected. You might ask, how can something be both? How can it be a wave and a particle at the same time? No one fully knows. What we do know is that the photon does not choose one or the other until we measure it. Until then, it holds both possibilities at once. It carries light across space. It delivers energy to plants and solar panels. It helps us see, yet we do not fully understand it. Now, imagine the scale we are talking about. These quantum players are so small, you could fit billions inside the width of a human hair. This is the quantum world, a place so tiny that the usual rules of physics begin to bend and twist. In the big world, if you kick a soccer ball, it moves in a clear path. You can measure how fast it goes and where it is at any moment. You can predict where it will land. But in the quantum world, things do not move in straight lines. They move in clouds of possibility. A particle might be here, or there, or both, until you check. This is why quantum effects do not show up in our daily life. The small stuff plays by different rules, but once many particles come together, their strange behavior starts to cancel out. The weirdness fades. Things become more predictable.
That is why a soccer ball acts like a soccer ball and not like an electron. To understand just how small these particles are, let us try a comparison. Picture a grain of sand. Now shrink an atom down to the size of that grain. The nucleus, the part with nearly all the mass, would still be smaller than a speck of dust inside it. The electron cloud would be like a wide, empty football stadium with a tiny pebble at the center. Most of an atom is empty space. Even more, these particles do not behave like tiny versions of large objects. They are not small versions of baseballs or pebbles. They belong to a different world entirely. A world where position and speed cannot be pinned down, where particles jump through walls, where two particles can become linked across space and change together instantly. This is why quantum physics matters. It shows us that the world we live in is not the full story. Underneath the surfaces we see, there is another layer, a deeper one, with different rules, a world of constant motion, constant uncertainty, constant wonder. Classical physics tells us how the big world works. It helps us build bridges, cars, and spaceships. But it fails when things get too small or too fast or too hot. That is when quantum physics takes over. It steps in and explains what classical physics cannot. One of the key differences is that classical physics is predictable. If you know where something is and how fast it is going, you can figure out where it will be later. But quantum physics is not about certainty. It is about probabilities. It tells us what might happen, what is likely. It gives us a set of possible outcomes, but it never says for sure. Another difference is that classical physics is based on forces, push and pull, gravity and friction. But quantum physics is often about energy levels, about changes in states, about how particles interact with fields we cannot see. None of this is just theory. It has real effects. It powers the devices in your pocket. It helps scientists scan the human brain. It keeps time in the most accurate clocks ever made. It even helps explain how the sun shines. But before any of that, it starts here, with the players in the quantum zoo, the atoms, the electrons, the photons, the strange rules they follow, the way they refuse to fit into the boxes we try to put them in. This is only the beginning. Ahead lies more mystery, more wonder, more discovery. But remember this, the world is not what it seems. It is more, stranger, and more beautiful than we ever imagined. Imagine a quiet room, inside a simple setup, a beam of light, a thin wall with two tiny openings and a screen behind it. This is not a machine from the future. It is just a table, a light, and a couple of slits. Anyone could build it. But what happens next is not ordinary. It is not even logical. It is the start of the weirdest experiment in the history of science. This is the double-slit experiment, and it has confused, amazed, and challenged scientists for over 100 years. What begins as a simple test of light becomes a window into the strange world of quantum mechanics. Let us begin with waves. Think of water in a bathtub. Drop a pebble in it. The waves spread out in circles. If you put two pebbles in, two sets of waves ripple out. When they meet, something happens. Sometimes the waves join together and make a bigger wave. Sometimes they cancel each other out. This is called interference. Now imagine light as a wave. If you shine light at a wall with two slits in it, the waves go through both openings. Then, just like water, they interfere with each other. On the screen behind the slits, you do not see two bright spots. You see a pattern, bright and dark stripes. This is a wave pattern. This is exactly what we expect from light acting like a wave. So far, so good. Now take it one step further. What if you turn the light down? Way down. So low that it sends out one tiny bit at a time. One photon, a single particle of light. The idea is that each photon goes through one slit or the other, like a small ball flying through one hole. You wait. One photon hits the screen, then another, then another. Slowly, a pattern begins to appear. Not two spots, not random dots. The same striped pattern of interference. It is as if each photon goes through both slits at once, as if it interferes with itself. This should not be possible. A particle should go through just one slit, but the pattern says otherwise. It acts like a wave, even when sent one at a time. This is already strange, but it gets even weirder. Scientists wanted to know which slit the photon actually went through, so they placed a tiny detector next to the slits. Something to see which path the photon chose. And suddenly, everything changed. Now, when the photons hit the screen, they did not make an interference pattern. They made two spots, as if they were just particles going through one slit or the other. Not waves, no more stripes, no more interference. What changed? The only thing was that we watched. We measured. That was enough to make the pattern disappear. This is the observer effect. Just trying to find out what the photon is doing changes what it does. The act of looking turns it from a wave into a particle. Even though we are only watching gently, the photon behaves completely differently. Somehow, the photon knows it is being watched. That is the part that keeps scientists up at night. You might think this is just a trick of light, but the same experiment was done with electrons. Electrons are tiny pieces of matter, part of every atom. Not light, but stuff. They have mass. They carry charge. They are real. And guess what? The same thing happened. When electrons were fired one at a time through the double slits, they made an interference pattern, like a wave. But when someone tried to measure which slit each electron went through, the pattern changed. It disappeared, just like with photons. Even little pieces of matter seem to behave like waves, until they are watched. This is not just a weird trick. It is a serious question about what reality is. What does it mean when particles act differently depending on whether we observe them? Are they making choices? Is reality only real when we look? One of the strangest versions of this experiment is called the quantum eraser. In this version, scientists allow the photon to go through both slits and interfere with itself. Then, after it has already hit the screen, they decide whether to measure which path it took. Depending on whether they keep or erase the which path information, the interference pattern appears or disappears, even though the photon has already landed. It seems as if the choice to observe or not can affect the past. This is not just science fiction. These are real experiments, repeated, verified, discussed in the highest journals, and no one fully understands why it happens. Some people say the particle does not have a definite path until we look. Others say the wave and particle exist together until measurement splits them. Some believe many possible outcomes happen in parallel universes. Some say consciousness itself might play a role. No one agrees. But everyone agrees on this. The double-slit experiment is the heart of quantum mechanics. It shows us that the world at its deepest level is not fixed, not solid. It is built on probability, on chances, on things that might happen. We do not live in a clockwork world, we live in a quantum one. And the double-slit experiment proves it. This experiment changed physics. It changed philosophy. It made scientists question what it means to observe, what it means to know. It showed that even the smallest act of measurement has consequences. It told us that the universe may not be what it seems, that particles can be waves, that matter can interfere with itself, that looking can change reality. It started with 2 slits and a beam of light, but it opened a door, one we are still trying to walk through. In the year 1935, a man named Erwin Schrödinger wrote about a cat. But he did not mean to write about animals. He was trying to show something strange about the quantum world, something that didn't make sense, something so odd he had to use a cat, a sealed box, and a deadly trick to make the point. This is how the story goes. Imagine a closed box. You cannot see inside it. In the box is a cat. There is also a tiny bit of radioactive material, a very small amount. It might decay, it might not. Alongside it, there is a detector. If the material decays, the detector catches it. If the detector catches it, it triggers a hammer. The hammer breaks a small bottle of poison. If the bottle breaks, the cat dies. If the bottle stays sealed, the cat lives. Now here is the strange part. In the world of quantum physics, the radioactive material is not either decayed or not decayed. Until someone looks, it is both. It holds both possibilities at once. We call this superposition. The material is in a superposed state, decayed and not decayed at the same time. So what about the detector? If the material is both decayed and not, then the detector is also both triggered and not triggered. The hammer is both raised and dropped. The poison is both released and still inside the bottle. And the cat is both dead and alive. At least that is what the rules of quantum physics say. But that makes no sense. A real cat cannot be dead and alive at the same time. It must be one or the other. That was Schrödinger's point. He did not want people to believe in ghost cats. He wanted to show how ridiculous it was to apply quantum rules to big things. Things like cats, things we can see and touch. He was saying, look how strange quantum physics becomes when you stretch it too far. Now let us step back. What is superposition really? In the quantum world, particles do not have to be in just one state. An electron can spin clockwise and counterclockwise at the same time. A photon can go 2 paths at once. A particle can be in 2 places at once. That is what superposition means. It is not either or. It is both. Until someone measures. Measurement is where the weirdness hits. The moment we observe the system, the superposition ends. The particle is no longer in two places. It chooses one. The electron picks a spin. The photon lands on one path. The cat is found either dead or alive. This is called the measurement problem. Why does this happen? Why does looking force a choice? No one really knows. That is one of the biggest questions in physics. Some say the universe splits, that both outcomes happen, but in separate worlds. Others say consciousness plays a role, that a conscious observer causes the outcome to collapse into one. Some believe it is just the interaction with the environment that ends the superposition. This idea is called decoherence. Decoherence happens when a quantum system bumps into the outside world. Air molecules, light, heat, any interaction can disturb the fragile superposition. That is why we do not see large objects behaving like quantum particles. They are always touching the world around them, and that contact destroys the quantum behavior before we can notice it. But in labs, scientists have learned how to protect tiny systems. They can shield particles from the environment. They cool them close to absolute zero. They keep them isolated. In those perfect conditions, superposition can survive. In 2000, researchers used a device to trap a single ion. They kept it in two energy states at the same time. In another case, scientists made a tiny bit of metal vibrate and not vibrate at once. Quantum computers are also built on superposition. The bits, called qubits, can be both 0 and 1 at the same time. That is what gives them power far beyond regular computers. Another strange result of superposition is quantum interference. When a particle is in a superposed state, its possible paths can interfere with each other. If two paths lead to the same point, the waves can either add up or cancel out. This creates patterns, the same kind of patterns we saw in the double-slit experiment. But this only happens when the particle is not observed. The moment you look, the paths vanish. The interference stops. So what about the cat? The cat cannot be in a superposition. Not really, not for long. The box is not perfectly sealed from the world. Tiny bits of air, bits of heat. All these things interfere. They make the quantum state collapse long before you open the box. That is why cats are not quantum. That is why big things follow classical rules. Because they are too connected to the environment to stay in superposition. Schrödinger knew this. He was not saying the cat could truly be dead and alive. He was showing the limits of quantum thinking. He was asking, where does the quantum world stop and the classical world begin? That question still has no clear answer. The line between the quantum and classical is fuzzy. Some say it depends on size. Others say it is about complexity. Some say the environment decides. But no one has found a hard rule. Only clues. One thing is clear. The quantum world is not separate. It is the foundation. Everything comes from it. Even you. Even the cat. But as things grow bigger, their behavior changes. The weirdness fades. The world becomes familiar again. The rules become sharp and steady. Still, the mystery remains. The story of Schrödinger's cat is not about death or survival. It is about what it means to know, what it means to observe, what it means to be real. It tells us that reality might not be solid until we look, that particles might hold many futures, that the world is richer than we ever thought. In the silence of that box, there is a question, and it echoes through every corner of physics. Can something be in two states at once? Can truth wait to be seen? The cat is not the answer. The cat is the question. There is a secret in the universe, a thread so thin we cannot see it, a bond so deep it connects two things no matter how far apart they are. It does not care about distance. It does not wait. It acts faster than anything else we know, even light. This strange bond is called quantum entanglement. Albert Einstein hated it. He did not trust it. He called it spooky action at a distance. He thought it was too weird, too wrong. He wanted the world to make sense. In his view, everything should follow clear rules. One thing should lead to another. Nothing should happen faster than light. But entanglement broke those rules. It was the one thing that made Einstein uneasy. Let us begin with what entanglement means. Imagine you have two tiny particles. Maybe they are photons. Maybe they are electrons. You can create them together in a special way. When you do this right, they become linked, entangled. They share a connection that is deeper than anything else in physics. You can separate them. You can send one across the room or across the galaxy, but the connection stays. Now picture this. You measure the first particle. Let us say you check its spin. Spin is like a tiny arrow pointing up or down. You find the first one is pointing up, and instantly at that very moment, the second one points down, no matter how far away it is, even if it is on the other side of the universe. It happens without delay. That should not be possible. Information should not travel faster than light. That is one of the most basic rules in Einstein's theory of relativity. But entanglement does not care. It skips over space. It acts as if space is not even there. That is why Einstein called it spooky, because it is. Einstein did not believe the particles were truly linked. He believed that the problem was in the theory. He thought quantum physics was incomplete. Maybe, he said, there were hidden rules, hidden variables. Maybe the particles had already decided what they would be before the experiment. Maybe we just did not know those hidden instructions. To prove his point, Einstein and two colleagues, Boris Podolsky and Nathan Rosen, wrote a paper in 1935. It became known as the EPR paradox. In it, they argued that quantum mechanics could not be the full story. If it were, it would mean that reality was not real until you looked. It would mean that things far apart could affect each other without touching. They believed that something was missing, something deeper. For many years, the EPR paradox sat like a question no one could answer. The math of quantum physics worked perfectly, but no one could say if it was complete. Then came a man named John Bell. In the 1960s, Bell was a physicist working in Switzerland. He did something bold. He turned the EPR argument into a test, a real test, one that could be done in the lab. He wrote a mathematical rule called Bell's inequality. It was simple. If hidden variables were real, the numbers from an experiment would follow the inequality. If not, they would break it. Now, scientists had a choice. Do the experiment, see what nature says. In the following decades, researchers did just that. They built machines. They shot pairs of photons in opposite directions. They measured their spins. They ran the numbers. Again and again, they found the same result. The numbers broke Bell's inequality. The hidden variables were not there. The particles were not waiting with secret instructions. They were truly entangled. The link was real. This was one of the most important discoveries in science. It confirmed that the world is not local. That means things do not just affect their neighbors. They can affect distant things too. It confirmed that quantum physics, strange as it is, works, even when it feels impossible. This is called quantum non-locality. It is the idea that the universe is connected in a way we still do not fully understand, that the space between two things may not matter at the quantum level, that something happening here can shape something far away, not through a signal, but through a shared reality. Some people wonder if this means faster than light communication is possible. The answer is no, not yet, because the results of quantum measurements are random. You cannot control what you will get. You cannot use it to send a message, but the connection is still real. The effect is still instant. It is not a message, but it is a mirror. Today, scientists are using entanglement in ways Einstein never imagined. In quantum computing, entangled particles allow for faster processing and more secure information. In quantum cryptography, entanglement protects messages from spying. If someone tries to intercept the data, the entangled state is disturbed. The system knows. It breaks the link. That means it is safe. In some labs, researchers are even working on quantum teleportation. It does not move matter, but it moves information. The state of one particle can be transferred to another instantly using entanglement. This may one day help build a quantum internet, a network where data flows not through wires or radio waves, but through the deep connection of entangled particles. All of this began with a simple question. What happens when you measure one part of a pair? The answer took decades to find. And even now, we do not fully understand why it works. We only know that it does. Over and over again, nature shows us that it is not what we expected. It is stranger. It is faster. It is more connected. Einstein may not have liked entanglement, but he helped us see it. His challenge forced science to dig deeper, and in that digging, we found something amazing. A hidden thread in the fabric of everything, a mystery that links the smallest particles across the widest spaces. Quantum entanglement is not just a weird trick. It is a clue, a sign that reality is built on relationships, that particles do not exist alone, that everything might be tied together in ways we are only beginning to see, in the quiet space between stars, in the flicker between atoms. The thread of connection holds, silent, instant, unbroken. Imagine standing in front of a thick wall. You run toward it and slam into it. Nothing happens. The wall holds. That is what we expect. In everyday life, solid things stay solid. You cannot walk through doors unless they are open. You cannot pass through brick, wood, or steel. That is how the world works. But in the quantum world, particles do not always agree. They sometimes do the impossible. They sometimes pass through barriers. Not by breaking them, not by finding a hole, but by being on one side, then appearing on the other, as if the wall was never really there. This strange event is called quantum tunneling. To understand why it happens, we have to remember that tiny particles do not follow normal rules. They do not act like marbles or billiard balls. They behave more like waves, soft, spread out, blurred. A quantum particle is not just in one place. It exists in a range of possible places. We call this its probability wave. It is like a cloud that stretches across space, showing where the particle might be. Now think about what happens when that wave hits a barrier. In classical physics, a barrier is a hard stop. If you do not have enough energy, you cannot get past it. It is like a hill. If you do not have the strength to climb over, you stay stuck. But in quantum physics, the wave does not stop right at the barrier. It leaks into it. It fades, but it keeps going. The wave gets weaker inside the wall. But sometimes, if the wall is thin enough, the wave continues through to the other side. That means there is still a small chance the particle can be found on the other side of the barrier. That is tunneling. The particle never climbs the hill. It does not go over. It goes through. This is not a trick. This is not science fiction. It is something that happens all the time. In fact, you would not be alive without it. Take the sun, for example. The sun shines because it burns hydrogen into helium. This happens deep in its core. But for that process to work, tiny hydrogen nuclei must come very close together, close enough to stick, close enough to fuse. But there is a problem. Each nucleus carries a positive charge, and positive things push away from each other. This creates an invisible wall, a repelling force. According to classical physics, the nuclei should never get close enough to touch. The hill is too steep. They do not have enough energy. Yet the sun burns. It shines every day. The reason is quantum tunneling. Even though the particles cannot get over the barrier, their wave spreads through it. A few of them tunnel through. They fuse. The sun keeps going. The light we see is powered by a quantum effect. This same tunneling is used by scientists on Earth. In the 1980s, engineers built a tool called the scanning tunneling microscope. It lets us see individual atoms, not with light, not with lenses, but with electrons. They bring a tiny metal tip very close to a surface, just a few atoms away. The tip and the surface do not touch, but the electron waves stretch across the gap. Some electrons tunnel through the space. By measuring how many make it, the microscope maps the shape of the surface, atom by atom. No other tool can do this. Only tunneling makes it possible. Now think about modern electronics. The tiny chips in phones and computers use switches called transistors. These are built from layers of material. Sometimes the layers are so thin that electrons can tunnel through them. If the layers were thicker, the electrons would stop. But when they are thin enough, the waves slip through. This is both a problem and a benefit. On one hand, tunneling can cause errors in circuits. Electrons get where they are not supposed to be. On the other hand, engineers have learned to use tunneling to build special devices. One example is the tunnel diode. It uses the tunneling effect to allow current to pass in unique ways. It switches faster. It works at lower voltages. It is small and efficient. It only works because of quantum weirdness. There is more. Some scientists believe tunneling may even play a role in life itself. Inside cells, certain reactions need particles to move from one place to another. Sometimes the energy needed is higher than the particle has, but the reactions still happen. Researchers think quantum tunneling might be helping. In plants, the process of photosynthesis is very efficient. It moves energy quickly and smoothly. Some studies suggest that tunneling may guide the movement of energy through the system. The wave-like behavior of particles helps the plant use light more effectively. In the human nose, scientists have wondered how we can tell smells apart. One theory says that smell may involve quantum tunneling, that particles in the nose may detect vibration by tunneling through barriers in a molecule. These ideas are still being tested, but they show how deep tunneling may reach, from stars to cells, from machines to breath. Quantum tunneling reminds us that particles are not locked in place. They are not stuck to simple rules. They explore, they drift, they leak through. The world at the smallest level is flexible, open, uncertain, alive with possibility. It also teaches us something about boundaries. What looks like a solid wall may not be solid at all. What seems impossible might still happen, given time, given the right conditions. The quantum world is full of quiet escapes, silent crossings, surprising journeys. We live in a world built on such events. You are reading this because of chips made with tunneling. You are alive because the sun burns with tunneling. Life may think and move and sense with the help of particles walking through walls. It is easy to forget this, to trust the feel of things, to believe that barriers are forever. But nature is not that rigid. The quantum world shows us that even a wall can be a doorway. Close your eyes for a moment and picture empty space. Imagine a place with nothing in it, no stars, no dust, no light, just silence and blackness. That is what we used to believe empty space was, a perfect vacuum, cold, still, dead. But now we know that is not true. Space is not empty, not even close. It is alive with energy. It ripples, it buzzes, it holds the deepest secrets of the universe. Beneath everything you see lies something hidden and powerful. It is called a quantum field. This is the world of quantum field theory. To understand it, we must change how we think. We are used to seeing the world as made of particles, tiny building blocks, atoms, electrons, protons, photons, like marbles or grains of sand. That idea works for a while, but it is not the full story. The truth is deeper. Quantum field theory tells us that particles are not the most basic thing. Fields are. Invisible fields spread across space. They are everywhere. They fill all of reality. And particles are not little pieces floating in those fields. They are tiny ripples, waves, blips of energy in the fabric. Think of a calm pond. Throw a stone in. Ripples spread out. Now imagine a field as that calm pond stretched across the whole universe. A particle is like one ripple in that field. Just a little vibration, a local disturbance, nothing more. But that ripple is what we see, what we measure, what we call a particle. Every type of particle has its own field. There is an electron field, a photon field, a quark field, even gravity has a field. These fields never go away, even in deep space, even in perfect darkness. They are still there, waiting. Now let us talk about the quantum vacuum. In classical physics, a vacuum is empty, no matter, no light, no sound, nothing. But in quantum physics, the vacuum is strange. It is never really still. Even in the quietest patch of space, the fields are shaking. Tiny ripples form and vanish. Particles appear and disappear. This is called the quantum vacuum. It is like a restless sea, always moving. These tiny pop-ups are called virtual particles. They are not full particles. They do not last. They show up for a tiny moment, borrow energy, then vanish again. They are allowed to do this because of the uncertainty principle. It says energy can come and go as long as it happens fast. These ghost particles cannot be seen directly, but their effects are real. One of those effects is called the Casimir effect. Imagine placing two metal plates very close together in empty space. Nothing should happen, but something does. The virtual particles outside the plates outnumber those in the narrow gap between them. This creates a pressure. The plates get pushed toward each other. No one touches them, but the vacuum does. It is one of the strangest forces ever measured. It proves that even nothing is something. These constant tiny jitters are called quantum fluctuations. They are not errors, they are features, built-in noise of the universe. They shape the early moments of the cosmos. When the universe was just born, these fluctuations helped matter clump together. That clumping formed galaxies, stars, and planets. Our whole sky is a result of tiny shivers in ancient fields. Now we come to one of the most famous fields of all, the Higgs field. For many years, scientists wondered why particles have mass. What gives something weight? Why does a photon have no mass, but a proton is heavy? The answer came from the Higgs field. This field fills the universe, just like all the others. But it does something special. As particles move through it, they interact with it. Some feel more resistance. That resistance is what we call mass. The more a particle interacts with the Higgs field, the heavier it is. If a particle ignores the Higgs field, it stays massless, like the photon. This idea was tested in the Large Hadron Collider. That is a huge machine under the ground in Europe. In 2012, scientists found the Higgs boson. That is the ripple in the Higgs field, just like a photon is the ripple in the electromagnetic field. The Higgs boson proved the field is real. Without the Higgs field, everything would be massless. There would be no atoms, no chemistry, no stars, no people. It gives the universe its weight. So what does all this mean? It means that the world we see is not built from solid things. It is made from shifting waves, from ripples in hidden fields. It means that space is not empty. It is a stage where invisible players perform the dance of existence. A photon is not just a bit of light. It is a pulse in the electromagnetic field. An electron is not a dot. It is a small shiver in the electron field. What we call particles are only the surface. Beneath that surface is a world of motion, quiet, constant, complex. And somehow all these fields weave together. They form the deep fabric of everything. We are part of that fabric, our atoms, our thoughts, our lives. Quantum field theory is hard, but its message is simple. The universe is not made of things, it is made of possibilities, of patterns, of energy and change. It is not solid, it is alive. The fields stretch across time and space, and in their ripples the story of reality unfolds. Quantum mechanics is strange. No one debates that. It works better than any theory we have. It makes accurate predictions. It powers technology. It explains how atoms behave. And yet, we still do not know what it really means. We can describe what happens. We can write the math, but we do not agree on what that math is saying about the world. So, over the years, many scientists and thinkers have come up with different ideas. These ideas are not different in their results. They all give the same answers when we do experiments. What changes is the story we tell about what is happening beneath the surface. These stories are called interpretations, and the debate is still open. The most famous and widely taught one is called the Copenhagen interpretation. It started in the early 20th century with Niels Bohr and his group in Denmark. According to this view, quantum particles exist in a cloud of probabilities. They are not in one state. They are in many at once. But when we measure them, the cloud collapses. The particle picks a value, a place, a spin, a direction. In this view, the act of measuring is special. The observer is important. Before measurement, the system holds all possible outcomes. After, it shows only one. That is why a particle can be both here and there. But once we look, it chooses. This idea became the standard way to teach quantum physics. It is clear, it works, but it raises hard questions. What is a measurement, really? Why does looking change things? Does the particle really not exist in one place before we look? Not everyone was happy with these questions. One of them was a young man named Hugh Everett. In 1957, Everett suggested something bold. What if all the possible outcomes happen? What if the wave never collapses? What if, when you measure a particle, the world splits? This became known as the many worlds interpretation. Imagine flipping a coin. In one world, it lands heads. In another, it lands tails. Both results exist, but each in a separate version of reality. According to Everett, the universe is constantly branching. Every quantum event creates new paths, new worlds. This idea sounds wild. It feels like science fiction. But it uses only the math we already have. It removes the need for collapse. It removes the need for observers to play a special role. It treats the whole universe as a quantum system, always evolving, always splitting. Some scientists like this because it keeps the rules simple. It makes everything follow the same laws. No magic moments. But it also means there are countless versions of you, of me, of everyone, all living different lives in different branches of reality. Others found this too much. David Bohm, another brilliant physicist, had his own answer. Bohm believed in hidden order. He created something called the pilot wave theory. In his view, particles always have a position. They are real. They move. But they are guided by a wave. This wave contains all the information about the possible outcomes. The wave spreads out and tells the particle where to go. It is like a map. The particle follows the map, but the path is not random. It is determined. This idea is more like classical physics. It brings back a sense of cause and effect. But it requires something extra. The pilot wave moves in a space larger than our 3 dimensions. It is harder to test. That is why it never became the main view. But it is still studied, still respected, still possible. Then there are ideas that make the observer even more important. Some scientists and philosophers have wondered if the mind plays a role. That consciousness is needed to collapse the wave. That reality does not take a fixed shape until a conscious being looks. This is the consciousness-based interpretation. It is not very popular in physics, but it has been discussed by thinkers like Eugene Wigner and others. It suggests that our minds are not outside the system. We are part of the measurement. Without us, the world stays in a fog of possibilities. It is hard to test this, and it opens deep questions. Are dogs observers? Are cameras? Does the moon exist when no one looks? Most physicists prefer to avoid such questions, but they are still part of the story. There is also the transactional interpretation. This one comes from John Kramer. He had a different idea. What if waves do not just move forward in time? What if they also move backward? In this picture, when a particle is sent, a wave goes forward to the detector, but the detector also sends a wave backward in time. The 2 waves meet. They form a handshake. That handshake decides the outcome. The process is complete. It is a strange idea, but it fits the math, and it offers a way to explain quantum effects without collapse, without observers. Some like it because it treats time more symmetrically, but again, it is hard to prove. Then we come to decoherence. This is not a full interpretation by itself, but it helps explain why the quantum world looks normal at large scales. According to decoherence, quantum systems lose their special properties when they touch the environment. Heat, light, air. Any contact spreads the information. The system becomes mixed. The wave spreads out and fades. It no longer shows interference. It starts to act classical. Decoherence does not solve everything. It does not tell us why we see only one outcome. But it shows how quantum behavior gets hidden, how superposition dies out, why cats are not both dead and alive. Finally, there is a newer idea. It is called cubism, short for quantum Bayesianism. This view says that quantum mechanics is not about the world itself. It is about what we believe. It is a tool to help us make bets, predictions, decisions. The wave function is not a real object. It is a personal belief about what will happen. Each observer has their own wave function, their own perspective. It is like playing cards. You do not know what the other player has, but you make choices based on your own knowledge. Cubism says that quantum mechanics works the same way. This is a very different way to think. Some like it because it avoids deep puzzles. Others think it avoids reality altogether. So why do all these ideas matter? Because they shape how we see the world. If the many worlds idea is right, every moment branches into new universes. If the Copenhagen view is right, Reality does not take shape until we look. If the pilot wave view is right, particles follow hidden paths. If consciousness matters, then your mind is shaping reality. If cubism is right, there is no reality, only beliefs. These are not small differences. They touch the heart of existence, of identity, of truth. Quantum mechanics gives us answers, but it also leaves us with questions. Many worlds, one world, no world until we look. We do not know which is true, but we keep searching. Quantum physics is not just a theory locked in books. It is not just about particles and waves behaving strangely in dark labs. It is already here. It is part of your daily life. It hides in your pocket. It moves through your home. It even helps doctors look inside your body. We live in a world shaped by quantum rules, whether we know it or not. Take light, not just sunlight, but lasers, barcode scanners, remote controls, fiber optics, eye surgeries. All of these depend on one simple quantum idea. When electrons in an atom jump from a higher energy level to a lower one, they release light. But not just any light. This light is precise. It has a certain color or wavelength. A laser takes this idea and controls it. In a laser, many atoms are pushed to excited states. Then, when one drops back down, it triggers the others to drop too. The result is a beam of light that is narrow, strong, and perfectly in sync. This is called coherent light. You see it in laser pointers, in DVDs, in eye surgery tools, all from quantum leaps. LEDs work in a similar way. Instead of glowing hot like old bulbs, LEDs use materials that release light when electrons fall into lower energy levels. They are cool, they are efficient, they last longer. That is quantum at work again. Now think about your phone or your computer. The chip inside it is not just a flat piece of plastic. It is a tiny world of electrons moving through channels thinner than a human hair. In some parts, those channels are so narrow that electrons do something strange. They tunnel through barriers. Not over, not around, through. This is quantum tunneling. It makes modern transistors possible. Without it, our chips would stop shrinking. Our devices would stop getting faster. The digital world moves forward on a quantum road. But quantum tools do more than help us see light or use computers. They help us see ourselves. Inside a hospital, there is a quiet machine. It hums, it scans, it sees through skin and into tissue. This is the MRI machine. It does not use radiation. It does not cut or poke. It uses quantum spin. Spin is a property of particles like protons. It is not spin like a top, but it acts a little like it. When you put these particles in a magnetic field, their spins align. Then you send a pulse of energy. The spins flip. When they return to normal, they release energy. The machine detects that. It builds a picture from those signals, soft tissues, bones, tumors, all from the way quantum particles respond to magnetism. Now imagine a clock that never loses a second in millions of years. This is an atomic clock. It does not tick with gears, it ticks with atoms. Atoms like cesium or rubidium. These atoms have a natural rhythm. When they switch between two energy levels, they absorb or release microwave radiation. This frequency is so exact that it can be counted. That count becomes time. GPS depends on it. Satellites use it to tell your phone where you are. Without quantum precision, your map would be useless. But quantum effects also protect. In a world full of hackers, we need ways to keep information safe. Quantum cryptography offers something new. It uses a rule no one can break. In quantum physics, you cannot measure a particle without disturbing it. This means if someone tries to intercept a quantum key, the act of spying changes the key. The receiver sees the change and knows the message has been tampered with. This is not just good security. It is perfect security, the kind only nature can provide. This is already being tested. In some countries, quantum networks send secure data between government offices. In the future, we may have a quantum internet, one that cannot be hacked, one built not from cables, but from entangled particles. Quantum computers are the next great leap. Our current computers use bits. A bit is either 0 or 1, that is it. But a quantum computer uses qubits. These are quantum bits. They can be 0, 1, or both at the same time. This is called superposition. It means they can hold more information, do more things at once. Qubits can also be entangled. This links them in a deep way. When one changes, the other does too, no matter the distance. That link helps solve problems faster. In certain tasks, quantum computers can outperform any regular machine on Earth. They are still in early stages. They are sensitive, hard to scale, but progress is fast. Researchers are building better qubits, more stable systems. In time, they may crack problems that today seem impossible. Drug design, climate models, encryption, supply chains, all may be transformed. Quantum sensors are another growing tool. They use quantum properties to measure things with extreme accuracy: gravity, magnetic fields, time, rotation, even tiny shifts in position. These sensors help submarines navigate without GPS. They help archaeologists find buried ruins. They help scientists detect earthquakes before they strike. They are not science fiction. They are being built and tested now. And this is just the beginning. Future technologies could change everything. Quantum radar could detect objects hidden by clouds or darkness. It could see through noise and confusion. Quantum batteries might store more energy in smaller spaces, charge faster, last longer. A quantum internet could connect cities, continents, and maybe even satellites with total security. None of this would be possible without the strange rules of quantum mechanics. Rules that once seemed useless, or just weird. Rules about particles acting like waves, about being in two places at once, about knowing less the more you look. These rules are now the tools we use to shape the future. We used to think the quantum world was too small to matter, that it stayed hidden in atoms, in shadows, in mystery. But now we know better. The quantum world is not separate from ours. It powers our light, our machines, our medicine, our communication. It gives us new eyes, new clocks, new hope. We stand on the edge of something big. A revolution not built on wires but on wonder, not on metal but on mystery. Quantum technology is here, and it is only getting started.